So yeah, I will be. I'm Rémy Neveu, and I will be talking about OMP task in LLVM. So first, the different tasks we can encounter in OpenMP. So we got the classical task. We got the classical tasks that are asynchronous on executing on the user threads. Then we got two type of offloading tasks. The synchronous one, the synchronous one, and the asynchronous version with the no wait. Now the workflow of LLVM with OpenMP. So we got the classical front-end optimization path, then back-end. But for OpenMP, we are adding the runtimes. So one runtime for the multi-threading and one runtime for the offloading. The offloading part is the libmp target. Because we are adding runtimes, we also need to add runtime calls to the front end. So with the LLVM libcobgen. Now I will try to point out where to find the different component of OpenMP in LLVM. So first, we got the clang, the OpenMP clang part that will be in the clang code gen, and it will. It is divided between the libmp and libmp target runtimes. The libmp target runtime got the GPU is ending by GPU, and they are calling to the OpenMP library, front-end OpenMP library, which is common with the Flang front-end. Then we got the optimization that we can find in the transform of the transform. It can be useful to point out that for this optimization, not a lot are concerning the task. The task part is mainly for the classical OpenMP. And then the two different runtimes are in OpenMP runtime for the libmp and the OpenMP libmp target for the offloading part. Now I wanted also to talk about task execution. So all the different threads are trying to execute the tasks. So we can find this algorithm in the runtime of OpenMP in the KMP tasking file, which is the main file for the task in OpenMP. So to be a bit more precise, it's in the I will describe more or less the KMP execute task function. So here I represented a team of threads. The thread, the priority queue that is common to the whole team, and another queue that is specific to each thread. And I wanted also to present first how the priority queue is executing. So if we got one task in the priority queue, the thread will try to get it with the KMP get priority task, then execute it. If there is one task if by executing this task, we are resolving one dependency from another task, and this task does not have any more dependency, we will push it either in queue of the queue of the thread or the priority queue, depending if the task got some priority or not. Then, if there is no task in the priority queues, the thread will try to execute their own task. But if there is no task in their queues, like for the second thread, they will try to steal it to another thread. So they put it in their queue and execute it. So that was for the classical task. For the target task, it's a bit different because target tasks are more or less embedded in a classical task. So they will try to execute the same way. But once we try to execute them, we will call for the kernel in the device, and then wait for the response of the device to tell it finished executing. The issue here is that all this waiting time is more or less a waste of time for the user thread. So the hidden helper team has been introduced. So what it does is that the user team is giving the target task to their corresponding either helper thread, and then the either helper thread will execute this target task and communicate with the device. The main point here is that because we are removing some the idle time from the user thread, and while trying to have a new team that is a bit lighter weight for a bit which is a bit lighter weight. Finally, I also wanted to talk about the task structure. So it can be found in kmp.h, and it's used so in kmp tasking and kmp task depth. So in fact, it's not one but two structures. So we got the kmp task, which is the real core of the data for the task, and then the task data is more the metadata around the task. To detail it, so kmp task got the private variables, the routine of the task, but also it's a priority on the destructors of the task. While the task data got the ID, some flags, which team and thread the task belongs to, and also if there is if the task is inside another task or got another task inside itself, as well as other runtime function. Then I wanted also to present some work from another team, which is the PPC team at the Barcelona Supercomputing Center. So they propose a new directive, the task graph directive. So when this directive is called, we will start by we will start to register the different tasks, and once we go another time on it, we will skip all the runtime calls and all the dependency resolution, and just replace the task graph and gain some performance with that. And thank you.
All right, we've got another couple minutes for questions. So, you know the drill. Microphones in the middle. Yeah, over there.
So regarding your task graph, do you have a offloading task in it or just post task?
Right now, it's only the classical tasks.
Okay.
I'm personally working to try to use it for target tasks.
And that will give a subgraph or something so that
Sorry?
the helper threads will be doing the target task still, or?
Sorry, I didn't get your question.
No, when you're offloading
Yes.
a target task, a task, right?
Yes.
Is the helper thread still going to use?
Yeah,
You're going to use the helper thread to do
that's the
that.
point of still using the hidden helper thread to improve even more.
But how will you handle no wait or something in that?
Sorry.
For task.
So the no wait at the asynchronous part. So if we are using the no wait part, we can even we can try to register where we are doing on which device we are sending and when we are sending it, okay. And just doing all the way when we can. On that fast.
Thank you.
Then one more quick question.
So if I understood correctly, the point of the record and replay mechanism is to reduce runtime overhead.
Yes.
Do you have any sort of number showing what the result is?
Not in this presentation. I think the team that did that got a paper on it, some improvement.
There will be a paper. Okay.
Yeah, there is a paper.
There is a paper with more details. Got it. Thank you.
Cool. Let's give our speaker another hand.